Thanks a lot. So since I'm the last formal lecture before I get started with the technical stuff, I just wanted to take the opportunity again to encourage us all to give a round of applause to the organizers, Veronica and Tom, for putting together this wonderful school, and everyone on staff as well who's been helping, Ethan, Alex, Tom, Oliver. So if we can all like unmute ourselves for a second and just please give a round of applause to everyone.
I want to thank all the lecturers and all the students for wonderful, well, all the lecturers for a wonderful job and all the students for active participation. It has been great fun.
Okay, great. So yeah, let's start the last lecture. So what I wanted to do today for the first part was just to really briefly finish up some aspects about the local operators in my two twisted mirror theories that we left off with last time. And I'm gonna be a little bit brief, and because I just kind of want to tell you the results and give you a flavor for them, because these things have been discussed beautifully in many places, and I'm happy to give references to all kinds of lecture notes. And the canonical reference, if you want to see more details about any of the stuff that I'll be telling you about in the first part of the talk today, is a huge textbook called Mirror Symmetry, and you can't miss it. And if it's in a room with you, you can't miss it because it's an enormous textbook and it has all the details you could possibly want. So I'll start with wrapping up about the local operators there, and then I want to move to some aspects of these kinds of stories that are a little bit underappreciated or less well known, at least relative to the stuff in the first part of the lecture, and also stuff that has some interplay with things that people are thinking about actively in research these days. So I hope that it'll be a little bit weird, a little bit more fun and unusual for the remainder of the lecture, just to kind of give you a flavor for some stuff cropping up in modern mathematical physics. Okay, so last time we left off with our two twisting supercharges, QA and QB, together with a choice of twisting morphisms that left these two supercharges respectively to be spin zero operators with respect to a new twisted Lorentz symmetry that I called 1' of L. And so in the context of string theory, say with Calabi-Yau targets, this gave us two ways to produce a topological field theory from the original 2D2,2 sigma model that we started with. And these two twists are exchanged under the mirror automorphism of the super algebra that we discussed last lecture. And so in particular, we're interested in a situation where we're studying the A twist on a sigma model with target some Calabi-Yau X, and the B twist on the theory with its mirror target X tilde, where remember the Hodge numbers of the theories were exchanged under mirror symmetry. And the Hodge numbers are related to the dimensions of the moduli space of Kähler and complex structures of these two manifolds. So this is a duality that's exchanging some geometric information on the two sides. Good. So remember that in a twisted theory, in our twisted theories, the operators that we call physical, the physical local operators, are going to be those that are annihilated by our twisting supercharge. And so we want to ask, what are the Q closed operators in the original sigma model? And that will furnish the space of local operators in the twisted theory. Good. And as we saw before, and as I've mentioned before, whenever you have a fermionic symmetry, be it a supersymmetry or a BRST symmetry, when you focus on the Q symmetric or Q closed operators as your physical operators with respect to these twisted theories, that automatically involves studying not just the Q closed operators, but the Q cohomology. Because once you're doing QFT, you automatically land on Q cohomology because, as we proved last time, the Q exact things become trivial in all the correlation functions. So physical operators in twisted theories, once again, are labeled really by Q cohomology elements. Good, so let me just tell you what the local operators for the A and B twists are. So let's start with the A twist, why not? And let's imagine that our theory is a nonlinear sigma model whose target is some Kähler manifold M. And mostly I'll be focusing on Calabi-Yau manifolds. So we can take, we looked at some of the terms in the action last time. We had a Kähler potential term and superpotential terms or twisted superpotential terms. And to describe the theory that I'm interested in, these sigma models with Calabi-Yau target, we can just study a suitable Kähler potential built from multiple chiral multiplets and their complex conjugates. So we don't have a superpotential that we need to worry about. We can take it to be zero. And we're studying, again, a theory of just multiple chiral multiplets and their complex conjugates. And I won't need to write it down explicitly for what I'm going to tell you about today. So you should just have in mind that there's a bunch of chiral multiplets in the game with some interactions. Okay, and we can take all the chiral multiplets to have vector and axial R charge equal to zero. Remember, we talked about preserving these symmetries, at least classically last time. So these charges will do the job. And that means that the scalars forming the bottom components of these chiral multiplets will also have charge zero. But the fermions, the fermionic superpartners, will still have non-zero R charges. They'll have charges plus or minus one, depending on the R symmetry, because they're compensating for the transformation of the Grassmann coordinates that they're multiplying in the chiral multiplet, as we wrote down for the action of these symmetries last time. So in the context of these sigma models, the scalars furnish this map from the sigma model to my target. I think there's maybe a little bit of a delay when I'm writing on my iPad versus when it appears on your screen. So I hope that's not too confusing, but let me know if it gets really bad and we'll try to figure something out. And the superpartner. Oh,
So far,
sorry?
so good.
So far it's okay? Okay, good. And the fermionic superpartners, of course, are worldsheet spinners prior to the twist. And they're valued in the pullback of the holomorphic tangent bundle on M, or the anti-holomorphic tangent bundle on M if we're dealing with a complex conjugate. So if you don't really like geometry, it's not too important to understand all the details of this. But they have some interesting index, they have some interesting geometric interpretation on the target space, and before the twist, they're just spinners on the worldsheet. Now, after we apply the A-twisting morphism for all the chiral multiplets, well, as I said, I've chosen everything to have charge zero, so my scalar fields are still scalars after the twist, but some of the fermions also become now worldsheet scalars. And in particular, so after twist, psi minus and psi bar plus are now scalars. And the other two theories, their spin, or the other two fermions rather, psi plus and psi bar minus, become holomorphic and anti-holomorphic one forms on the worldsheet. Because remember, after the twist, I'm just modifying the spin of all the operators by their R charge with respect to the vector symmetry. So I'm going to ignore the one forms for now. Okay, so now I need to ask, what are the Q-closed operators, say in the A-twisted theory? So I can use either my superfield representation of the action, or I can expand everything out in components. And if I write everything down, it's pretty straightforward to determine the action of all the n equals 2,2 generators on all of the component fields in these chiral multiplets. And it'll depend on the interactions and everything else. And the details aren't too important. But remember that a general supersymmetry variation can be expressed in terms of all four supercharges multiplied by corresponding anti-commuting parameters that are usually called epsilon. So in order to extract the action of QA on the component fields from the action of all of the charges on the component fields, you just set the spinner parameters. So set spinners associated to Q plus and Q bar minus equal to 0. Those, because remember QA is given in terms of the other two supercharges. And you set the spinner parameters associated to Q bar plus and Q minus equal to each other. So ultimately, you're just restricting the SUSY variation on all the component fields that you're looking at to this delta that I'm writing down here. And then you can just look at the action on the component fields, do the computation, stare at it, look for the things that are 0 under that transformation, and try to convince yourself that they're not exact, that they're closed but non-trivial. And the ones that, well, okay, let me tell you the ones that survive when you do this exercise. So we need to look at, in particular, Lorentz invariant local operators. So whatever survives, we know has to be built from the scalars, which in the twisted theory are psi and psi minus and psi bar plus. And any other putative scalars that we might try to construct in our twisted theory, well, they'll generically have some indices, you might have some derivatives acting on them. And to make a Lorentz scalar, you're going to have to contract those indices with the worldsheet metric. But we know that in our twisted theory, our worldsheet metric is Q exact, and so all of the other possible options are also Q exact. So they're totally trivial in cohomology. And it's easy to argue that a little bit more rigorously. So in the A model, all of the local operators that you can construct are going to be of a general form like this. So I have some function of phi, and the i's are my space-time indices, because all of these fermions, remember, are still taking values in my target space, and the scalars are still giving me a map to my target space. Obviously, I have the right number of fermions to contract all the indices. You get the idea? So all of our local operators look something like this. And if we think a little bit harder about the geometric interpretation of these fields, and in particular the fermions, and I encourage you to do this on your own, you find that there's a nice geometric interpretation of the fermions in this twisted theory. In fact, they transform like and can be identified with forms on the target space, holomorphic and anti-holomorphic forms on the target space M. And indeed, you can check that the twisting supercharge can also be identified with the de Rham differential D. So the space of local operators in the A model is nothing but de Rham cohomology in my target space. So that's some nice geometric thing that's perhaps familiar from other contexts. And it can be graded by form degree because, well, we can distinguish one forms from two forms and so on, and that comes from the U1R symmetries that grading is preserved. Okay. Now, once you have a space of local operators, you want to compute correlation functions with them, of course, and I'm going to be especially telegraphic about this part because I want to get to fun stuff, and these things also quickly become rather technical, and so I'm not going to be able to do the detailed computation work for you in real time. But you can study the action in the A model as a prerequisite to inserting further local operators in the path integral and trying to compute correlation functions. And you find that the action can be written as a Q exact piece plus an additional piece. So first of all, the fact that I can write the action as almost a Q exact thing is good. I mean, the stress energy tense, certainly if my entire action is Q exact, then that's a sufficient condition for my stress energy tensor to be Q exact, which we wanted in these twisted topological theories. The other term that's not Q exact actually is a topological piece. So we do see that none of my topological invariance of my twisted theory is spoiled by it. And this extra piece, it turns out, is an integral over the complexified, so complexified by the B field, complexified Kähler class on the target manifold. And we've seen the complexified Kähler class of, say, the torus before. This is a more general thing. And the integral is over the image of the worldsheet given by the map from my scalar fields. And it only depends, it turns out, on the homology class of the map. So explicitly, you can see that already you can anticipate that this A model really only depends on Kähler moduli, not complex structure moduli. We see the Kähler class, but all of the complex structure dependence gets folded into Q trivial stuff. So the A model is not only topological on the worldsheet, but it's kind of half topological in target space. It knows about half of the geometric data of the target, but not the other half. Because remember, the moduli space, as we talked about last time, and also as Irene talked about, locally at least factorizes into the Kähler and complex structure part. So it really is kind of like a half topological theory in target space. And you can, again, use use this form of the action and try to compute correlators of local operators. And you can use the localization principle that I kind of sketched last time, but I didn't really have time to explain. But the punchline of that was that you should study the Q invariant field configurations. And those turn out quite powerfully to give you exact results when you try to compute these correlation functions. And in the case of the A model, you find that the Q invariant field configurations, when you study this action, are given by holomorphic maps. So that's already quite a dramatic simplification. It turns out that there's still actually a pretty non-trivial moduli space of holomorphic maps to integrate over when you compute correlation functions of these operators. So it's not a completely trivial thing. In fact, there's a lot of subtleties, and I'm not going to go into it, but that's still already a much more well-defined space to deal with than than trying to integrate over all possible field configurations of the full path integral. So you can get exact results in this way. And at genus 0, using this localization onto holomorphic maps, you can compute correlation functions for my local operators, so my so-called twisted chiral ring elements, to use the terminology from last time. And using geometric identifications I sketched above, you can find that in the t goes to infinity limit, where t is this parameter multiplying my topological term, the correlation functions reproduce classical intersection numbers of cycles in the target space, so a nice geometric quantity. But these actually get modified for finite n by what are called worldsheet instantons. And you get something called quantum cohomology, or quantum corrected intersection numbers, which are deeply tied to mathematical invariants called Gromov-Witten invariants, which very, very roughly speaking are like counts of holomorphic maps, since we've localized onto holomorphic maps from the worldsheet into the target space. But the A model we found is pretty non-trivial, and it's actually quite an industry in algebraic geometry to compute these Gromov-Witten invariants in their own right. And that's one of the reasons why it's nice and very useful, in fact, to pass to the B model. Well, let me do that now and tell you what the analogous computation for the B model will get you. So in the B model, again, with target a compact Calabi-Yau, no superpotential, do the same kind of exercise. And let me show you what the QB closed operators after twisting are. Well, of course, I still have the scalars. No surprise there. But now 2 new fermions become scalars with respect to the Lorentz group. And more precisely, you find the following combinations of these fermions are now Q-closed. So you see I get the other 2 fermions are now scalars with respect to this twist, and I'm just defining some convenient new variables to actually capture which combinations of them are Q-closed operators after the twist. So I'm going to write things in terms of these variables eta and theta instead. And again, these have geometric interpretations. The eta i's, very similar to the fermions in the A model, can be identified with anti-holomorphic forms in the target space, but the thetas, well, you see they have a lower index, and more naturally they transform as holomorphic vector fields in the target space. And if you look at their action under Q, well, Q now, QB, can naturally be identified with the Dolbeau operator, the operator that raises only the anti-holomorphic form degree by +1, but not the holomorphic form degree. And so again, we have a geometric interpretation of the space of local operators in the B model. And it's something called the Dolbeau cohomology of polyvector fields, which I'll write in a fancy way, but locally, it's very similar to, how's the, okay, there we go. It's very similar to an expression like this, where I just replace, instead of holomorphic forms and anti-holomorphic forms, locally I have a bunch of anti-holomorphic forms and a bunch of vector fields. And in the case of the B model, actually the entire action turns out to be Q exact. And the Q invariant field configurations that result from doing a localization type analysis are actually constant maps to the target. And they receive no interesting corrections because the entire action now is folded into this trivial piece. And that's very powerful because the space of constant maps into the target space are just point-like maps. So if you like the moduli space of all such maps, all point-like maps to the target is just the target itself. So now correlation functions in the B model after localization reduce essentially to doing ordinary integrals over my target manifold of some geometric quantity that I called polyvector fields. And if you don't like the geometry, the details don't particularly matter. The important thing is that localization in the B model has given me a simple classical geometry problem that I can compute very explicitly. And by mirror symmetry, I can actually use classical computations in complex geometry in the B model, translate those results to the mirror A model side, which is much harder to deal with, and use the B model computations to help me extract things like Gromov-Witten invariance, or more generally, just answers to those computations, which would have been much harder to do, dealing with those moduli spaces of holomorphic maps and all of the complications that the A model brings. So I'm translating some interesting enumerative geometry question on the A side to a simple classical complex geometry question on the B side. And physically, I have at least one side of the duality that's very easy and tractable for me to work with and that I can compute with explicitly, even though I'm not doing the computations in detail for you today. Great. And again, although it's not obvious from the way I've written the action, but the B model is topological on the world sheet, but it's again half topological in space-time. It does depend on the complex structure of the manifold. And it's not obvious from what I've written, but one way to see it is that, well, in order to integrate something that has a bunch of vector fields, I can wedge in a copy of the holomorphic volume form that we also talked about last time, which locally, remember, is on a D-fold is like this. So I can wedge in the holomorphic volume form to eat up all of those vector fields that I don't know how to integrate and, well, contract the indices. And wedging in the holomorphic volume form will not only enable me to integrate over the manifold, because I'm translating polyvector fields into ordinary differential forms, but the holomorphic volume form also depends on the complex structure. So that's kind of one way to at least find it plausible that the B model is a complex structure dependent thing. And it definitely does not depend on the Kähler structure. So that was, of course, going through everything a little bit quickly, mostly just because I'm excited and I want to get to fun stuff before the lecture series is over. But let me just pause and ask if anyone wants to ask anything at this point. Because from here, I'm going to move a little bit away from local operators and talk about extended operators and other things.
I have a couple of questions. So one of them is H11 and H21 do not uniquely determine the Calabi-Yau, right?
Correct.
So there can be degeneracies. So in that case, does mirror symmetry tell you, given one Calabi-Yau, what its mirror dual will be, or do you need to extract that data from somewhere else?
Well, good. So when I say that, so the Hodge numbers don't uniquely determine the Calabi-Yau, but in particular, what does that mean? The Calabi-Yaus admit these complex and Kähler deformations. So it's not really just a map of a single Calabi-Yau with a single Ricci flat metric and its mirror that I'm trying to match, but a whole family, a geometric family on both sides that I'm trying to match. And indeed, mirror symmetry is kind of mapping these geometric families of Calabi-Yaus into one another. But there are also various geometric ways to construct mirrors on both sides. And ways to write sigma models for them as well. I haven't told you sort of the techniques to write sigma models, but there are lots of nice ways to construct mirror pairs, actually.
And the other question was, I've heard this before, but I just want to make sure. The quantum cohomology structure is how does that differ from the classical cohomology ring? Is it just the differential or both the differential and the product?
Great question. Great question. Differential. Well, sorry, which differential do you mean? Just
when you go from the classical cohomology ring to the quantum cohomology ring, do you change just the QB or the differential, or do you also need to change the wedge product between the different forms?
The wedge product will also get corrected.
All right, thank you.
Sure. Okay, so now I want to tell you some. So as I said, the stuff that I kind of blazed through just now, you can read about in a bunch of classical sources, and I have many really excellent ones, and please ask me if you want me to share those with you. But like I said, I want to move on to aspects also of this mirror story, but things that are applicable to more general twisted theories that are a little bit less standard than just looking at the cohomology of some supercharge, producing a ring of local operators, and then computing the correlation functions by localization. They're good things to know, but it's, you know, I want to teach you some things that come up in more modern context as well. But for the moment, I can illustrate some of these ideas by sticking with the A model and the B model, including these choices of twisting morphisms. And so where do I want to go from here? So we just saw local, or if you like, zero form operators in Q cohomology. I want to get some non-local operators now. And it turns out that from the local operators, there's an interesting class of extended operators that I can obtain using a procedure called topological descent. And this is, again, this is not a new thing, but its importance is being appreciated more, and it's maybe a little bit less familiar. So we applied these twisting morphisms, and they made our supercharge of interest, either QA or QB, into a scalar. Other supercharges in the theory under the same twist, you can easily check, become one forms with respect to the new twisted Lorentz group, U1 prime L. So a basic super Poincare algebra in arbitrary dimension, after you've applied some topological twisting morphism, well, is going to look like this. And actually, let me just write down the only non-zero, the only interesting non-zero term in the super algebra that will be relevant for us. Namely, we have one supercharge that's a scalar, anti-commuting with the other supercharges, some collection of supercharges that remain in the theory, which are now one forms, and they anti-commute to the generator of translations in, say, the x mu direction. So given a Q closed operator, local operator O of x, let me define its one form topological descendant. And then I'll explain why I would feel motivated to define such a thing. So there's the one form descendant, but in fact, I want to define higher form descendants for essentially as many dimensions as I have. So for the A and B models, I can go up to 2 forms because I'm on a 2-dimensional worldsheet. But for a general D-dimensional topological quantum field theory, at least one that comes from twisting a supersymmetric quantum field theory, I can have, or I guess I'm using K here, I have up to K form descendants. Okay, now, what the heck are these things? Well, they're not Q closed, first of all, but they satisfy a pretty nice relation. They're almost Q closed. In fact, they're Q closed up to a total derivative, where D is just the exterior derivative on my spacetime. So these equations that I've just written down actually give a set of recursive relations for all of the descendants amongst themselves. And you can check that these set of equations I wrote here indeed give solutions to this Q of OK equals D of OK minus 1 equation. So for example, Q of the one form operator by definition, is this. And then I can just use the superalgebra and the translation operator to relate it to a total derivative of the one-form operator. So because the Q variation of the descendants, the topological descendants are total derivatives, what I can do is integrate them over non-trivial K cycles without boundary to obtain honest Q-closed extended operators. So let me call them O of gamma, where gamma labels the closed cycle over which I'm integrating, say, the K form, or, if gamma is a D cycle, I'm integrating the D form descendant over it. If I tried to integrate them over some more general K chain with a boundary, I wouldn't get a Q closed thing. Q acting on the operator would give me the descendant operator supported on the boundary. So I have to stick with closed cycles to get Q closed things on the nose. And Stokes's theorem plus the defining equations for the topological descendants, it actually tells us that O gamma only depends on the homology class of gamma. So these kinds of funny non-local operators actually famously first appeared in Witten's study of Donaldson invariance of four manifolds, and he studied two-form descendants wrapped on non-trivial two cycles of four manifold, did some cool geometry that, of course, I can't tell you about today. But in a two-dimensional theory, like the B model or the A model, I'll have, in general, non-trivial one and two form descendants. And I can study these on world sheets of various topologies with non-trivial closed cycles. Because remember, the twisting morphism means that I can now define my theory on Riemann surfaces of arbitrary topology while preserving my now scalar supercharge, because the covariant derivative of the scalar of the spin zero epsilon parameter is going to be zero now. So for example,
could I ask
in
a
the
question?
B model, yeah.
For this whole topological descent, do you need more supersymmetry than the minimal supersymmetry to define the twist?
More supersymmetry than the minimal supersymmetry to define the twist?
Like, is this a result of having extra supersymmetry than what you would need to just define the twisted theory in the first place? Because you're using
so
extra
I've used,
supercharges.
No, good. So I've used the twisting morphism such that one of the supercharges is a scalar and the rest are one forms. But I haven't used, but otherwise I've just used only this most generic, this really basic superpoint Carré algebra. That's all I'm using as input for this part.
Great.
Sorry, I think it's finally now boxed. I know you guys are on a time delay. Okay, and similarly for the A model, also has one and two form descendants, and just replace Q minus with Q bar minus to get the A model descendants. So now you can go ahead and study correlation functions of these integrated descendant operators along with the local operators. I won't go into that, but I want to tell you first of all that a special role is played by the descendants of top form degree. So in this case, it would be the two form operator, because they govern non-trivial deformations of the original TQFT. Why? Well, a deformation term comes from adding some D form term to the action. And the integrated descendants, at least at the level of the action, well, they're Q closed, so they look like perfectly good deformations of my TQFT that respect the topological invariance of the underlying theory. So I can add terms. I called my world sheet sigma. I'll stick with that notation. So I can add terms like this to my action with arbitrary coupling constant out in front. And these are good deformation terms, indeed, because the resulting thing is Q closed, at least to first order. The extension to all orders in perturbation theory is a very interesting thing. So for example, in the B model, I can think about my local chiral ring elements. Remember, products of chiral ring elements stay in the chiral ring. So I could imagine looking at a chiral ring element that I'll write as delta W phi, where I've chosen the U1 charges of the local operators such that if I put them in a superfield, they would correspond to an honest to goodness deformation of the superpotential. Like, let's say I'm focusing on just symmetry preserving deformations that have the nicest possible properties. So indeed, at the level of superspace, if I were just trying to go ahead and deform my theory, Well, I would write down in superfield notation an action like this for some delta W in terms of my chiral multiplets. And I can integrate over the superspace coordinates. And again, these are nice equations, nice things to check yourself, and they're not too hard. So the lowest component will be my little chiral ring element here. And this is precisely the two-form descendant of the bottom component operator. Similar manipulations, if I tried to deform the B model by a D term or a twisted F term, you can do exactly a computation like what I just did and find that those are QB exact. So the only non-trivial B model deformations come from superpotential terms, F term deformations. And a mirror statement to this one that you can also show in the same way holds that in the A model, the two-form descendants of the so-called twisted chiral operators govern deformations of the model. So you get twisted F term deformations, but the D and F terms are QA exact. And so in practice, since we consider, these finite numbers of local F term or twisted F term deformations in any given theory, we see that the twisted correlation functions, the correlation functions in our twisted theories, depend only on a finite number of parameters. Or a more fancy way of saying this is that the descendant operators of the chiral or twisted chiral ring elements span the tangent bundle of the moduli spaces in my theories. In the Calabi-Yau case, where the moduli space is locally factorized into complex and Kähler deformations, the corresponding descendants in the B and A model span the corresponding tangent directions of the two factors. The B model sees half and the A model will see the other half. And of course, by contrast, general correlation functions in the full untwisted theory can depend on infinitely many parameters. So this is really a nice simplification to study. And just to make an extremely cryptic remark that I won't explain anymore in these lectures, but just to kind of maybe tantalize you with interesting things, theories of deformations of mathematical structures, like well-behaved quantum field theories, twisted quantum field theories, or more general things, which are often called formal moduli problems in mathematics, turn out to be profoundly connected to homotopical algebras. If I have time at the end of the lecture today, I will say something about these algebras, though not through this connection. There's a very deep relation there that I can't do justice to in these lectures. But connections between deformations of TQFTs and things called L-infinity algebras actually have been pretty well understood in D = 2. And the generalization to higher dimensions and with other kinds of twisted theories is a subject of active research. And to make an additional cryptic remark, I'll just tell you that the connection between these things, moduli problems and higher algebras or homotopic algebras, goes through something called the Maurer-Cartan equation, which captures the condition for a nilpotent differential in a theory to remain nilpotent after a deformation is applied. And of course, this lecture series is all about nilpotent differential operators or nilpotent operators and their cohomology. So that doesn't explain the connection, but maybe with these words, you can sort of see that something cool is going on where all of the pieces will start to fit together into some beautiful larger structures. And again, I hope to tell you actually about an A-infinity algebra by the end of the lecture, but we'll see how far I get. I have till 5:15 today?
Yes.
Okay. Actually, I may get to it. If I get to it too early, it means I'm rushing too much, but y'all can always slow me down.
35 minutes.
Great. Okay. So, so if I have some theory on some manifold of non-trivial topology, now I have some interesting class of operators and these integrated descendants that I can study on some non-trivial closed cycles. What if I was studying a twisted theory in flat space, where there are no non-trivial cycles to integrate my descendants over? Or more formally, the non-trivial cycles are the point class, and so I can only study local operators. Well, it turns out that descendants are still useful, and they still have interesting consequences, even if I'm not putting my manifold, or even if I'm not putting my twisted field theory on manifolds of interesting topology, although that's a good thing to do. They can still have a non-trivial consequence in flat space. In fact, sometimes the non-trivial consequence that they have in flat space goes away if you put the theory on more non-trivial manifolds. In fact, they induce so-called higher products in the operator algebra of the twisted theory. So what I'm going to do now is explain one of these higher products in a very, very simple, the simplest possible context today, called the secondary product. So this is an additional product, an additional interaction between local operators in my twisted theory. And the descendants give that to me. So as we've been discussing for the past couple lectures, in any d-dimensional topologically twisted theory, we of course have a collision product on local operators coming from just bringing these two, say, chiral ring elements, for example, together. And the topological invariance arguments that we've detailed tells us that this product doesn't depend on the position of the operators or on how we bring them together from which directions. You know, we're kind of in the simplest possible state here. So we have some product of local operators. We've already talked about that a little bit. And I'll just write them with square brackets around them to remind you that things here only depend on the cohomology class. I'm studying Q-closed operators in a theory with a fermionic symmetry. To define the secondary product, we do something maybe kind of straightforward, something you might have imagined trying to do. Let's place a local operator, one of my Q-closed local operators O1 at some point x. Let me imagine surrounding it with a little ball with boundary a sphere of d-1 dimensions. And remember, I'm always in Euclidean signature, so d dimensions is just d Euclidean dimensions. And let me integrate the descendant, the d-1 form descendant of some other local operator around this sphere surrounding it. So remember, the descendants are just some smeared operator. And I have one point-like operator, and then I have a smeared operator kind of surrounding it in this ball. And everything here in sight is topologically, I mean, all the, there can be no interesting non-Q exact dependence on the radius of the sphere. So, you know, just imagine shrinking everything down so that the integrated descendant kind of collapses on top of the point-like operator. Again, everything is topological. And so again, the result of doing this secondary product operation actually can be viewed as representing a cohomology class. All the same kinds of Q exactness arguments go through in just the same way as they did with the local product. And I'll do a little example computation in a second. But so the original product, so this product and the secondary product, together endow our twisted theory or our Q cohomology with the structure of what's called a graded Poisson algebra, which just means that it's an algebra that has a compatible associative product and a Lie structure as well. And so I define the secondary product. I'll write the secondary product to be given in terms of a little bracket, curly brackets, which is called the Poisson bracket. Which is just a Lie bracket. It satisfies the Jacobi identity, though I won't prove that today in these twisted theories, and it behaves nicely with respect to the original local product that we started with. And when I say nicely, I'll write it down, but the formal way to say it is that it acts like a derivation on the local product, which just means it has the following property. So there's a certain sign here, a plus or minus sign that depends on the fermion number of the operators and the dimension of the twisted theory, but won't bother writing it down. So it's a derivation of the associative product that we had already seen. So let's do an example. And we'll stick with our favorite example, the 2dB model. But now we'll consider it on a flat world sheet. So I don't have any string application in mind. I'm just viewing this as some supersymmetric field theory in two flat dimensions that I've twisted, and I'm going to study the property. But you can still think of the field theory, say a sigma model with target some Calabi-Yau, on just a flat world sheet, just the complex plane. So we already deduced that the space of local operators is isomorphic to the Delbow cohomology of polyvector fields on the target space. So we've seen that before. And because the chiral ring elements, well, let me just say, it's because the B model doesn't get any non-trivial corrections like the A model did. It doesn't get any of these so-called worldsheet instanton corrections. The primary product, the local product on cohomology, is just a usual geometric wedge product on polyvector fields. So it's just an uncorrected, purely geometric thing. And if you don't like polyvector fields, don't worry about it. They're very much, I mean, maybe you are comfortable with vector fields and forms, and we just have a bunch of them together and they have a wedge product. This is just some purely classical thing in geometry. And it really depends, again, only on the cohomology class. And I'm just emphasizing that by putting square brackets around everything. Now, the secondary product actually has a rather famous application in worldsheet string theory. It's called the Gerstenhaber bracket, for those that really like old-fashioned worldsheet string theory, as I do. But geometrically, there's already a well-known geometric bracket on polyvector fields that this secondary product will turn out to reproduce, called the Schouten-Nijenhuis bracket on polyvector fields, which is a Lie bracket on polyvector fields that generalizes the Lie bracket on ordinary vector fields, which maybe you've seen in other contexts. But you know, if you don't like geometry, that doesn't matter. So let's see what the secondary product actually is in the B model. And let's just take our target to be Cn, just n-dimensional flat space. So we have a theory of n free chiral multiplets, because I like doing easy computations. And again, we're in the B model, so we have our twisting supercharge. And the vector supercharge in the previous notation was given by the other things. So I can write it as a vector with components given by the supercharges that became spin 1 under the B twisting morphism. So on flat space, life is as simple as possible. Geometrically, the only non-trivial vector fields are just, or polyvector fields, are just non-trivial holomorphic functions and ordinary holomorphic vector fields. No interesting higher stuff of higher form degree. And let me just for notation and to emphasize the fermionic origins of these things, use again theta for the field that corresponds to the holomorphic derivative on flat space. And so to get all the information about all of the polyvector fields, really I just need to get the secondary bracket on theta and phi. Phi is generating all the holomorphic functions, theta is generating the holomorphic derivative. So this is kind of the non-trivial thing I need. Of course, I can also compute things between phi and theta, but I'll mention at the end that those are 0. So this is the only interesting non-zero product that I'm going to have. So let's just compute it, because it's kind of a simple and fun thing to do. Okay, so to compute the secondary product, let's say I have phi at some point x, and I'm surrounding it with, in 2 dimensions, it will just be a circle. I'm going to want the one-form descendant theta 1 to integrate. So I need the one-form descendant theta 1, which is just defined to be the action of the supercharge on theta I, multiplied by the form degree. I'm kind of folding that into my definition of Q. So everything's a free field theory, and it's easy enough to write down the free fermions and free scalars and components and just compute everything. So check this yourself, or believe me when I tell you that if I compute this and I just write it in terms of geometric things, I just get this, essentially star D of the complex conjugate field phi. And to go further with the computation, here's a useful observation. The exterior derivative of my one-form descendant, well, basically it's this. And this turns out, and again, you should check this by just writing down the free field theory action and verifying it. The exterior derivative of the one-form descendant is given by, is proportional, at least, modulo any factors and signs that I might have messed up, to the equation of motion for the scalar. So if we treat that as an operator, this equation of motion operator for the scalar, say with my coordinates z and z bar on the world sheet, then in any correlation function, the operator product between the equation of motion operator and the scalar operator itself is actually equivalent to inserting a delta function 2 form, as long as they're separate from any other operators in the correlation function. And that's easy enough to see. So let's just write it out. E to the minus s. It's my operators. So this I can just rewrite. So this is some standard thing in Euclidean CFT, or Euclidean QFT, pardon me. Many of you may have already seen this before, so apologize if watching me write out this manipulation is boring for you. But I just rewrite the first term, I get a sum of 2 terms, and then I can just integrate by parts and land on a delta function, this contact term. Okay, that seems nice. And indeed, now let's just plug everything into the definition of my secondary bracket. And again, I'll use square brackets to emphasize the cohomological dependence of these things. So you have some circle, a closed integral over a circle of my 1 form and my field. And well, let me just use Stokes' theorem to rewrite the integral over the circle instead to an integral over the disk that the circle bounds. And I think you can all see why I want to do this, because now I can just plug in the result that I just derived, insert that delta function, I just get, at the end of the day, a little Kronecker delta. So pretty simple product at the end of the day. And you can also obtain the result by flipping the order, descending on phi, and getting the same answer. And it's kind of nice to just sanity check that that works. And similarly, if you try to compute the secondary bracket between 2 phi's or 2 thetas, you would find that that vanished just because there's no contact term between the operator and the resulting equation of motion that appears in the same kinds of manipulations. And indeed, one can check also in cases with more non-trivial geometric targets that indeed the secondary bracket reproduces the geometric bracket on the natural geometric Lie bracket on polyvector fields called the Schouten bracket up to a sign. And again, one can also check more formally and more field theoretically as well that it satisfies all of the nice properties that we want it to have, like the Jacobi identity and blah, blah, blah. So the lesson here is that descendants, even on flat space, can induce new algebraic structures on the algebras of local operators and twisted theories. So here we obtained a new non-trivial binary or 2-to-1 interaction between local operators in the B model, which are just polyvector fields. So like everything else in the B model, it has a geometric interpretation as well. In the spirit of making cryptic remarks that you guys might find interesting in your future life, it turns out that if I didn't pass to cohomology, and I considered the full physical Hilbert space, but up to, applying this twisting morphism, if I didn't pass to the cohomology, and I considered integrating descendants on cycles that had boundary, so-called open chains, well, I get something that's not Q-closed, I get some boundary terms that didn't vanish. And it turns out that not only would I get a secondary product from considering these descendants, but I'd get a whole tower of non-trivial operations, not only 2-to-1, but actually n-to-1 for all n. And they would turn out to satisfy a structure called the relations of what's called an L-infinity algebra. So there's a tower of operations more generally, if you don't pass to cohomology, that map n-closed operators to general operators in the physical theory. So you get so you leave cohomology. You can't get this from the twisted theory. You can't get this from cohomology. But if you still just think of the original Hilbert space and you kind of pay attention to the action of Q above and beyond the action of everything else, and you just try to isolate what happens when you're studying the action of Q on things and the resulting products, that if you don't collapse everything to cohomology, you can identify some nice algebraic structures on the full Hilbert space. And mathematically, we would say that these are algebraic structures on the chain level. So before you pass to cohomology, but viewing your Hilbert space as some kind of graded space with a differential, where I'm singling out one of the supercharges. And I'll actually say a little bit more about this sort of thing in just a moment. Okay, so I'm doing okay on time. So what we've seen is that already algebraic structures in twisted supersymmetric quantum field theories can be extremely rich, and they can give all kinds of cool things. Let me also just briefly make a remark that in the more general twists of the sort that are getting a lot of play in research right now, the so-called holomorphic twists, you can get interesting secondary products as well. And for example, in holomorphic twists, since you get structures like vertex algebras, the corresponding holomorphic descendants induce what are called Poisson vertex algebras on those theories. So the structures generalize, and you get cool things that I don't have time to tell you about, but I'm happy to point to references where you can see some of these things worked out explicitly. In particular, there's a nice recent paper by Castello, Damate, and Gaiotto that do this in a 3D n equals 2 theory that has a mixed holomorphic and topological twist. So 2 holomorphic directions supporting a vertex algebra and 1 topological direction, for example. Good. So at the level of cohomology already, we found some cool Poisson algebra structure emerging in twisted TQFTs, and I focused on the simplest ones. And I've also hinted very cryptically that if you work with the Hilbert space as a graded chain complex with differential Q, I can get other stuff, L-infinity algebras, Homotippy algebras, or more generally what mathematicians call higher algebras. But it turns out that sometimes these non-trivial higher algebras actually can remain even at the level of cohomology. And these are pretty intricate and difficult structures sometimes in both mathematics and physics, although not as difficult as they may appear. So what I'd like to do is finish off these lectures by just making some basic remarks and illustrating in a simple physical context one of these so-called higher algebras, an A-infinity algebra. And so roughly speaking, an A-infinity algebra is like an associative algebra, but what one says is that it's associative up to homotypies. And similarly, L-infinity algebras are Lie algebras up to homotypies. And I'm going to just illustrate this in very concrete terms. So I'm not going to define formally what it means, but I'll just kind of tell you how this kind of structure arises and the sort of consequences that it has. So let me consider, in order to make these remarks and illustrate it a little bit, and hopefully convince you that these are actually not such scary things, and in fact, very interesting things, let me consider something even simpler than the 2-dimensional B model. Let me just consider any supersymmetric quantum mechanics as a 0 + 1-dimensional Euclidean quantum field theory. So before I introduce A-infinity algebras, I need to make a slightly simple definition of a slightly different object called the differential graded associative algebra, or DGA. So that's labeled by a pair of things, an algebra and a differential. So A is an associative algebra, and it has a differential, dA, that acts as a derivation of the associative product, which means that the differential satisfies the same relations with respect to the associative product as our secondary bracket did. You know, it behaves nicely, or it respects the associative algebra structure. So where can you get such an algebraic structure? Well, you can get it, for starters, from SUSY quantum mechanics, which just has a superalgebra given by a supercharge Q and Q dagger anti-commuting to the Hamiltonian. So if we have just some supersymmetric quantum mechanics, well, the operators in a SUSY quantum mechanics, in particular, I'll imagine that it's topological, although I don't have to be so strict necessarily. The operator algebra of the supersymmetric quantum mechanics will form an associative algebra A. So A is associative. So these are just the operators in my theory. And I'll assume that A is Z-graded. So in particular, I'll assume that there's a fermion number operator F. Sometimes I only need Z2 graded things, the fermion parity operator, but oftentimes in many interesting circumstances, I get more. Doesn't really matter. So I'll split up A like this, where A of J are the elements of the algebra, just satisfying this. Have eigenvalue J. And let me only think about or care about the action of one of my two supercharges, Q. Q commutes with a Hamiltonian, and it sends, by its natural commutator or anti-commutator action, the elements of AJ to the elements of AJ plus 1. Just like how the de Rham differential acts on differential forms, or maybe or how the BRST operator acts on components of different Gauss number. So we say that Q, formally one would say that Q is a derivation of degree 1 because it increments U by 1. And indeed, it acts as a derivation of the operator product. I mean, we know how supercharges behave. And in this formula, when I write the square brackets, I'm using a little shorthand to indicate what's called a graded commutator, just meaning that in this formula, my square brackets could be either commutators or anti-commutators, depending on the parity of, depending on the fermion parity of the operators that it's commuting or anti-commuting with. So what one might say is that with respect to this privileged supercharge Q, I would say that A is a DG algebra. A is a DGA. And the states in the Hilbert space as a representation of this algebra would be said to be a DG module for A. Just terminology if you come across it in life. So of course, in many of the applications that we've been thinking about in these lectures, we've been mostly interested in the Q cohomology or the half BPS operators, namely the elements of A, well, at least half BPS operators, the elements of A that satisfy this relation. And we've talked a bit about things, structures that arise on the level of their cohomology class. So that's what we've been talking about all this time. So what about A infinity algebras? So an A infinity algebra sometimes called a Homotippy associative algebra, is a chain complex, ADA, that's endowed with a family of operations called mu n. And the mu n satisfy a number of consistency relations among them. And it's not so hard to write down the general consistency relations that they satisfy, but let me not bother with that today. Let me remark for starters, just to give some intuition, is that if all of these operations, these n-to-1 operations mu n, are 0 when n is greater than or equal to 3, then A is an ordinary DGA. Mu1 is the differential, mu2 is the usual associative product, and so the structure kind of collapses to the basic thing that we just talked about. But it turns out that even the cohomology or homology of a complex can inherit the full structure of an A infinity algebra with non-vanishing higher operations. How does that happen? Well, you can define the complex that you're studying, where the algebra is given actually by the homology or the cohomology, and you just treat that as a complex with a trivial differential. You know, you've taken the cohomology, there's no interesting differential left, but formally you pretend, you just say, okay, well, the differential is 0 then, and formally I can apply the same kinds of mathematical definitions. The higher structures, by the way, that result when you study cohomology are called Massey products. Just the name. So what about in SUSY quantum mechanics? Why would this show up? Okay, so let's see it. Let's go back to our DG algebra with differential supercharged Q and its usual associative product. And we can pass to cohomology, which we've been doing, which we do all day. Well, mu1 is 0, as I've just told you, because there's no interesting differential anymore. We've taken the Q cohomology, we're ignoring Q dagger. No interesting differential left. And mu2, well, that's just the binary product on cohomology classes that got inherited from the associative product on A. So mu2 is inherited from A. Now, normally in an A infinity algebra, the next operation, mu3, so normally when you study A infinity algebras, I said they're homotopy associative. They're not, normally we like associative algebras, that the two different ways of multiplying things are equal to one another. A infinity algebras aren't associative on the nose, they're associative up to what's called homotopies. And normally, in an A infinity algebra, the difference, or what's called the associator, so like if I have mu2 on A and BC minus mu2. So this is 0 in an honest to goodness associative thing, mu2, sorry. Normally this depends on terms like this. So there's a bunch of, so mu3 governs the failure of mu2 to be associative, and it includes the differential kind of acting on all of the possible slots, and there's various signs that you have to keep track of. So I'm not going to bother with the formulas. Okay, so normally mu3 is the thing that kind of measures the failure of my product, my operator product to be associative. When I pass to cohomology, actually, this is still associative on the nose for trivial reasons. There's no differential. In cohomology, all of these terms on the right-hand side vanish, and I still have an associative product. But it turns out that I do still have interesting higher operations that generically non-vanish. And it turns out that all of these things do still satisfy the axioms of an A infinity algebra. And for today, I'll just tell you what mu3 is and illustrate that it's non-trivial. Take 3 BPS operators, A1, A2, and A3. More precisely, they're cohomology classes. And suppose that they satisfy that the product of A1 and A2 is 0 in cohomology, and the product of A2 and A3 is 0 in cohomology. So in the full physical theory, the products would be a Q exact quantity. And now we make a choice. So this is not a uniquely defined operation that I'm doing, but I can make a choice of operators that I call B12 and B13, such that A1 and A2, the product in the full theory is given by this. So these are some choices I'm making. And then I define an operator A1, 2, 3 in terms of these choices. I define it in this way. Oops. And if you just stare at it for a moment, this thing is Q closed by construction. So it is a good operator in cohomology. Of course, I have to argue a bit. Sometimes you have to check explicitly in a given theory that you don't end up with an exact thing, but it's at least by construction Q closed. So in particular, A1, well, in fact, you can argue that it's not exact. So in particular, A1, 2, 3 defines a non-trivial cohomology class. And so this product is some non-trivial map between where I take 3 Q-closed things, 3 operators in my cohomology, and I spit out a new operator in cohomology. And this is, so this is the Massey product, the third Massey product. And similar but more complicated formulas also hold and exist for the higher products. So in this kind of baby example of supersymmetric quantum mechanics, the higher algebra structure is like a kind of spectrum generating algebra for BPS states in this theory, or at least the half BPS states that are annihilated by Q. And I see I'm running out of time.
5 minutes.
5 minutes, okay. So in general, and that's great. So that's really what the technical stuff that I wanted to say. So let me summarize a bit and start making some closing remarks. So in general, I might start with some physical system that I can describe as a DGA by just paying attention to how supersymmetry plays with the Hilbert space on one side of a duality. And I might pass it through some duality map. And it turns out that if you start with the DGA on one side of a duality map, generically, you'll actually get a full non-trivial A infinity algebra on the other side. Mathematically, this is called Homotippy Transfer data. Again, the names and precise definitions are not important for anything that I'm telling you today. On the other hand, if you started with an A infinity structure on one side, often you can also map to A infinity algebras in general. There's also notions of A infinity morphisms between 2 A infinity algebras, blah, blah, blah. I mean, these are well-defined mathematical structures. There's a ton of understanding about how they map to other mathematical structures, and there's a huge literature that now you can play with and use that to try and understand, say, some supersymmetric quantum mechanics problem. So in these scenarios, say a DGA and an A infinity algebra that are related by some Homotippy transfer data, some interesting map, the things on the two sides of these maps are called quasi-isomorphic, which is a term that means isomorphic in cohomology. So generically in a physical theory, these kinds of A infinity products, so even before passing to cohomology, will depend on various physical choices, like how you choose to regularize the collision products when you bring operators together. Of course, in cohomology, everything's trivial. I mean, it doesn't matter how I bring them together. All that stuff kind of drops out. But in general, there are choices involved. And the choices mathematically correspond to physical choices. But when you pass to cohomology, the algebraic structures pass to isomorphisms on the nose. Okay, which is good, because when we're testing dualities, we had better hope that we get isomorphisms on the nose in the Q cohomology of my twisted theories. Now, there's a lot more to say about higher algebras, and I'm running out of time, but they show up ubiquitously in string theory. So I'm just going to tell you some places where they show up, and field theory as well. Quantization via the BV-BRST procedure, which I mentioned at the beginning of my last lecture. We mentioned BRST, and I told you a little bit about the generalization of BV. In general, yields something called BV algebra structures, which are very rich. Topological quantum field theories and closed string field theories associated to topological strings naturally come equipped with L infinity structures, which are like the Lie version of the A infinity structures that I introduced. And again, this is related to something called the Moore-Cartan equation that I cryptically mentioned earlier. In fact, the equations of motion in these string field theories associated to topological strings are given by Moore-Cartan equations. Going back to our old friend mirror symmetry, if I further enrich the mirror symmetry story by thinking about the addition of branes, so these are also extended operators, but they're not ones that I can get from local operators like the descendants, well, then mathematically, as you might imagine, the structure enriches considerably as well. In fact, on the B model side, you obtain something called a DGBB category, a DG category, and mirror symmetry maps this to an A infinity structure on the A model side. And actually, when you have branes, you deal with mathematical structures called categories, so there's even some more structure involved there, and it's very rich and beautiful. But in particular, the algebra structures pass amongst one another in a nice way under the mirror symmetry map. In recent works by Gaiotto, Moore, and Witten, who also studied 2D 2,2 theories, which you now know about, though they were focusing on massive Landau-Ginzburg theories in the A twist, and they were studying these on flat spacetimes, two-dimensional flat spacetimes, although they also studied the theories with boundary conditions and on strips. The authors explicated the A infinity structure that they get from fusing topological line defects in the two theories. They also obtained the secondary product of local operators in these theories. And more explicitly, they studied the theories at chain level and elucidated the full L-infinity structures on these kinds of theories. Enrichments and generalizations of L-infinity algebras are sometimes called ED algebras, and those appear in D-dimensional TQFTs. And the mathematician responsible for a lot of explaining the structure is Lurie. And finally, and I should have said this at the beginning, this lecture, at least part of the descendant content of this lecture, was based on a paper by Beam, Benzvi, Bullimore, Demofte, and Knightsky. And in addition to studying descendants in B models and other interesting contexts, they also study secondary products in twisted 3D n=4 theories. So there's field theory applications too. So now I'm really going to conclude and just summarize the general lessons from the whole lecture series, not just the stuff from today. So I hope to have hammered home the following kind of broad lessons. So cohomology, first of all, cohomology. That's the theme. It's a powerful covariant way to obtain either subspaces or quotients, for example, from imposing physical constraint conditions or from gauging various kinds of physical and mathematical systems. It's used ubiquitously in physics and mathematics. And both the parent chain complexes and the cohomology groups themselves can carry rich and intricate algebraic structures that relate operators or states in the twisted theories to one another. They organize the spectrum and the interactions for you. The algebras are generally so-called higher algebras, and we talked a little bit about Poisson algebras and Poisson vertex algebras and homotopical algebras as two examples of those kinds of higher structures. And we've seen that such cohomology problems appear frequently in twists of supersymmetric quantum field theories. In the context of string theory, twists on the world sheet gave rise to topological strings. We explored topological strings at genus 0, and they've been a source for powerful geometric equivalences like mirror symmetry. And I want to mention that more work is in progress using topological string theories and their associated closed string field theories to understand ADS-CFT and more recently aspects of celestial holography using techniques from higher algebra, in particular something called Cazul duality. And this work is done, work that I'm doing in collaboration with Kevin Costello. I also I briefly told you that supersymmetric localization naturally generalizes a mathematical subject called equivariant cohomology. So everything's cohomology, 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 and you can use it to compute a host of supersymmetric or BPS observables, including but not limited to observables in twisted theories that we studied. And BPS states, which can be isolated by this twisting procedure, are also deeply related to the geometry of moduli spaces, and they govern deformations of physical theories or in families of inequivalent vacua in a powerful way. Indeed, these special subspaces of our physical Hilbert space can span tangent space to the moduli space, for example. And deformation theory, again, as I cryptically hinted, also connects again to higher algebras in ways that are being explored and are still only partially understood. And the last remark, and then I'm done, is that the web of string dualities, more broadly, is extremely vast and intricate. It passes through compactifications and perturbative and non-perturbative dualities, which we've touched on, as well as many branches of mathematics, which we've also tried to touch on a little bit. And although many of the strong weak dualities that we've discussed give us access to various corners of the string theory landscape, so far our dualities are still useless when the coupling constant is of order 1 in all duality frames, where we don't have a description where the coupling is weak. And we still need a deeper understanding of string theory away from limits that are perturbative in some duality frame. I'm hopeful that mathematical structures can help us get a better handle on string theory more broadly. And I hope that if this is a field that you're interested in exploring, and if these are the kind of techniques that you're interested in applying to these sorts of physical problems, I hope these lectures have empowered you or inspired you at least a little bit to start to dive into this work. And give you a handle on some of these ideas. So with that, I am done. It's been a pleasure and an honor to lecture, and thank you very much for your attention.
Thank you for wonderful lecture series. Very nice. So, any questions right now for Natalie? has been a lot to digest.
I have a question if nobody else is going. So these algebras originated before quantum field theories, right? So I believe Stashev was the one who came up with this stuff. Where was he using it? So where did they show up in geometry?
Yeah, good. So they show up geometrically in many places, and in particular in the geometric questions that the A-model string theory naturally probes, they show up. But yeah, historically, I remember that he was studying them in his PhD thesis, but to be honest, I forgot what his PhD thesis was on, or if he was just developing the structure without particular applications in mind. Yeah, that's a question better posed to a mathematician, but definitely they are, they certainly show up in lots of geometric contexts.
Could I just ask a quick technical question?
Sure.
If you have a local operator O of some ghost number,
Yes.
what's the ghost number of its descendants?
Oh, good. Yeah, so the descendant will up the ghost number of the local operator. So of course you can apply descent many times to get operators of higher and higher form degree. And so depending on your conventions, if say your supercharge or your BRST charge is ghost number 1, then when the descendant will, it will increase the ghost number by say 1 for the first descendant and on for the higher form descendants.
Great, thanks.
Oh, sorry. Well, okay. Normally in the conventions that I'm most used to and that appear in my papers, it actually goes the other way.
Good, yeah, that makes more sense.
There's cohomological shifts that I've suppressed in all my lectures, and I frequently mess up signs in practice, but yeah.
Other questions? Okay. All right, so in that case, we can stop the recording.